Thank you all for coming. Today I'm going to talk about how failure analysis of large components can be performed using the rising step load and residual stress analysis methods. This presentation is a joint effort between U.S. Corrosion Services, the Lou Raymond and Associates, and Applied Fracture Mechanics. And I want to recognize my co-authors, Craig Todd and Dr. Lou Raymond. Unfortunately, they were unable to make it in due to some extenuating circumstances, so I'm going to be presenting remotely. So what I'm going to talk about today is how you can use these different methods, including the rising step load test and the hole drilling method for stress analysis, as part of your failure analysis process. And some specific uses in hydrogen embrittlement, and then I'll more broadly discuss uses in other types of failures, including stress corrosion cracking, corrosion fatigue, sour corrosion, high temperature hydrogen attack, a number of different methods that have been evaluated using these methods. And what I'm showing in this graph is an example of the step loading method that's used for evaluating materials to determine their threshold for cracking and ultimately to evaluate their fracture toughness values. And in the bottom, I'm showing a sub-size specimen that's been removed from a large bolt. So the point of this is that we can take large structures, make numerous samples, and test them in a fast and affordable way that allows you to quickly evaluate their material properties. So the rising step load method is an analogous method that can be compared with the sustained load method that's been used for a much longer time period. And ultimately, the reason you would select to use them is this. They predict the same result, but the step loading method can provide that same value in a manner of hours or days as opposed to weeks. So in this particular example on the left side, you're seeing the rising step load and how it's applied to a material over a number of hours. And on the right side, you're seeing the sustained load method, in which the material is held at the same sustained load for 200 hours and then stepped up until fracture occurs. And this method is commonly used as ASTM F519, which is applied to a wide number of different aerospace components because it's helpful for preventing and ensuring that materials aren't susceptible to hydrogen embrittlement. So, here's an example of why you would pick the rising step load method. For a lot of materials, it can be performed in 8 to 24 hours. It doesn't require a large test frame. It can be in a tabletop size, and in fact, you can have several of them on a single table. It produces a quantitative value that we call HSR, which is the hydrogen stress ratio, or susceptibility ratio, And most importantly, it's highly reproducible, as compared to the sustained load method, which only gives you a pass-fail answer and doesn't have the same sort of reproducibility that you would get with the rising step load method. So some of the pictures I'm showing here are examples of stress corrosion cracking, pitting corrosion, and microstructure. And these will come into effect when you're looking at hydrogen embrittlement and other failure mechanisms. So the rising step load method started with analysis related to hydrogen embrittlement, and it's successfully been used in a number of aerospace and other applications. For example, failure analysis of the Titan launch vehicle for the Air Force, failure analysis of the F-111 jet, also for the Air Force, an analysis of the explosion of the Sansanina oil tanker, and related analysis of icebreaker blades for the Coast Guard. It's been used by Department of Transportation for railroads, by Department of the Interior for evaluating offshore structures and platforms, and by NASA for looking at bolts on the shuttles. And recently, one that many of you are probably familiar with is the Bay Bridge failure analysis, in which they evaluated 32 large bolts that failed due to hydrogen embrittlement as part of the construction process of the new Bay Bridge in San Francisco. Now, ultimately, with all of these, the root cause comes down to three things. You have to have a susceptible alloy, you have to have a high enough load, and a susceptible microstructure. And so really there's three dependent variables that all have an effect. The material, such as the steel along with its hardness, the environment, for example, whether it's in water, whether there's some kind of cathodic voltage or corrosion occurring, and then the stress, which could include both applied and residual stress. And if you change one of these, the others are going to change, and then you need to understand how those are going to affect your materials and how they perform. However, we're working to expand the use of the sustained load test to the step load test to a number of other methods that fall under the broad umbrella of environmentally accelerated corrosion, which can include a whole number of different things like stress corrosion cracking, sour stress corrosion, hydrogen embrittlement, corrosion fatigue, high temperature hydrogen attack, caustic embrittlement, liquid blistering, liquid metal embrittlement, etc. And in 1977, the National Bureau of Standards said specifically that stress corrosion, which is a broad term for environmentally accelerated corrosion, has not been brought to the point of enabling us to avoid or control the problem, and there's no basis for confidence that it will do so in the future. Fortunately, with the rise of the incremental step load method and residual stress analysis, modeling, etc., in 2022, we really understand environmentally accelerated corrosion much better. There's been enormous amounts of research with confirmed models that evaluate many of the different failure modes. And with new methods, we can rapidly understand and evaluate the susceptibility of materials to corrosion. And one advantage of sub-size specimens specifically is that it allows for testing of parts where otherwise you wouldn't be able to remove something like a CTOD sample, or where other samples are not feasible to be taken out of. So for example, C-rings can also be used in the step loading method, and that can be pulled from fairly small amount of material from a component. Or another example is in additive manufacturing. Specimens can be printed right along with the production parts so that you can evaluate their susceptibility directly and immediately as you're producing your components. And what this ultimately means is a drastic reduction in the cost and the time required to do analysis on components where otherwise you would have to build a full-scale model. So hole drilling is another method that's been applied to failure analysis successfully in many different ways. And the method for that is ASTM E837. It's a quick quantitative measurement, and it can be performed both in the lab or in the field. So what I'm showing you in the top right is an example of one of the strain rosettes that's used. And essentially what you have is 3 different strain gauges that are centered around a central hole. And the hole is drilled out while the strain is measured every few thousandths of an inch. And once you record enough data, you can take that and use the equations provided in the ASTM method to calculate quantitative numbers for the stress at different depths. And this can be really helpful because then you can see whether the material is under tensile or compressive stress, or if there are shear stresses there. And then all of that data can be put into models so that you can more accurately understand what's going on when a failure occurs. And on the bottom left side, I'm showing some examples. The strain gauges can be applied onto curved materials, onto flat materials, and they come in a number of sizes and shapes, so they can be used in a lot of different applications where normally it would be difficult to measure stress, and where other techniques like neutron diffraction or X-ray diffraction would be difficult to apply. Also, another advantage is this is a semi-destructive technique. It does leave a small hole in the part, but especially for thick components, the hole can be ground out and it can still be used or further evaluated. So to use stress analysis in your failure analysis, what you would do is identify and actually quantify the stress state at the areas of interest. So for example, in a weld, this measurement technique could be applied directly on the weld, in the heat affected zone, or near the weld. And in combination with step loading, which you can use to determine true fracture toughness values, this can be used to really accurately model the real world circumstances of how a failure is occurring. And ultimately, then we can take that data and apply theories that are related to the calculated stress and that connect that with the ability of the material to actually carry a load. So this process can be used in a variety of stress-related failures. And one other thing I'll note is that the hole size determines how deep the measurement can be. So these strain gauges can come in very small and much larger sizes, and you can get to a fairly significant depth, or you can do it in a very small location, but with a limited depth. So historically, environmentally accelerated corrosion tests have relied on sustained loads with long exposure times, and some examples are the F519 sustained load test that I mentioned before, the salt fog corrosion testing, G31, which is used for immersion corrosion, or bacterial growth tests. And for all of these, we've steadily been working to find faster methods that can do the same analysis. So with modern environmentally accelerated corrosion testing, we're replacing those older methods with new methods that provide similar but faster results, and in many cases are more quantitative. So for example, the Annex 3 version of F519 is the step loading test, which is a much quicker alternative. For traditional salt fog, you can replace it with cyclic corrosion, which is both more quantitative and more easily correlated with actual real-world conditions, and also occurs faster. With ASTM G31 type of tests, which require immersion for sometimes weeks or months, you can replace many of these tests with electrochemical testing, such as linear polarization resistance. And for evaluating microbial analysis or microbial corrosion, we can now use bacterial DNA tests that give us results in a matter of hours or days instead of having to wait much longer for bacterial growth tests to be completed. So really, there's potential for many similar options for stress loading, step loading, and for stress analysis, and that's part of the purpose of this presentation. So here's an example of how stress plays a role. When we do finite element modeling, we're relying on the modelers and how well they can understand and predict the material. And the root cause of many different failure modes comes down to the same thing as hydrogen embrittlement. It's a combination of microstructure, the stress, and the environment. And so with accurate stress analysis, you can confirm how much the internal residual stresses are contributing to the failure, or alternatively, you can build a mock-up and do stress analysis that can be applied with applied stresses, and you can see what the actual stresses are in the true constrained condition. And so this is an example on the left showing how finite element modeling was compared with actual testing and how well it matched up to evaluate the loads and materials. So the rising step load test has been used extensively in hydrogen embrittlement analysis, and one thing about hydrogen embrittlement is it's usually associated with intergranular cracking, but then again, not all intergranular cracking is truly hydrogen embrittlement. So to determine whether it really is or not, you can apply the rising step load test and determine the threshold for hydrogen embrittlement. And that can tell you whether the intergranular cracking really was related to hydrogen or if something else occurred. And furthermore, there's two different things that occur. There's internal hydrogen embrittlement, which is what we call it when it comes from processing, coating, fabrication, and so forth before it's been placed into service. And then there's external, and that can occur from things like fluids, from external sources of hydrogen, such as gases, but it can also occur from even corrosion processes, which can generate hydrogen as they're occurring. And another thing that's interesting is that sometimes hydrogen embrittlement and other failure modes occur under fairly low applied stresses where we wouldn't have expected them to happen. And why does that happen? Well, typically that can be because of residual stress, which is the stress left in the component after it's been fabricated or from processing. And so part of the analysis that you might want to do in a failure analysis is also to investigate the stress levels, and that's why hole drilling and other similar methods are helpful for determining quantitatively what the stress levels are. So here's an example of how hydrogen affects materials. On the left side, we see the hydrogen content compared to the charging time, which is going up dramatically. And then we also see that the fracture strength drops off substantially as the hydrogen content increases. And what that means is when you look at the fracture surface, you see the initial fracture surface is a fairly ductile fracture. And as the hydrogen content increases, it steadily becomes more and more intergranular fracture type of mode of fracture. And on the bottom left, again, we're looking at the UTS, the tensile strength of a material, and how it varies with the concentration of hydrogen. And as hydrogen concentration goes up, the tensile strength drops off dramatically in these materials. And again, you see a resulting change from ductile to brittle fracture. So with hydrogen specifically, the effect of hydrogen is it really has a dramatic reduction in the ductility of the materials. And it can actually brittle both single and polycrystalline materials. So while we typically think more often of steels and other things, this can also occur in single crystal materials, such as you might see in a blade from a turbine or other things like that. So here's an example of where subsized specimens using the rising step load test were successful in evaluating hydrogen embrittlement, and in comparison with a much larger full-scale testing. So on the left, I'm showing the schematic of the structure that was used to evaluate the Bay Bridge bolts. In this structure, there's an acoustic monitoring system to listen for fracture. There's a wet chamber where the specimens are loaded up. There's strain gauges that are applied to evaluate the stress over time, and then a transducer that's applying the load, and the parts are pulled until fracture. And due to the way this method was set up, it took roughly 30 to 40 days each, and the overall cost of testing was millions of dollars. In the end, what they found was the results were almost identical to what was determined using the rising step load test, with these much smaller samples that you can see on the right side. And so from a single bolt, the rising step load method was able to remove dozens of samples. And then because we're keeping the threads intact, we can accurately measure what the stresses are like in the real sample. And that gives you a way that you can really be sure that you're evaluating something that's similar to what a full-size test would be. And so this method is much less expensive, faster, but also produced almost the exact same results as the larger scale testing did. And then on the bottom right side, I'm showing an example of a C-ring specimen that's similar and can also be used for evaluating materials to determine hydrogen embrittlement or other corrosion mechanisms, and quantitatively determine how susceptible they are. There's another important thing that's useful to evaluate, and that is the effect of voltage on hydrogen embrittlement. So the HSR, which is the hydrogen susceptibility ratio, really shows the effect of hydrogen on how cracking occurs. And in this case, we're using it in comparison with voltage. So these same materials were made with small subsized specimens, and then a voltage was applied cathodically at different levels. And you can see as the implied potential gets more electronegative, the susceptibility ratio drops substantially. And so the 1.2 ratio that's shown on the left side corresponds to the 75% loading that would be used in the ASTM F519 type of test. So we consider in this case that to be the minimum criteria. And you can see as the material gets softer, the lower hardness materials like the 36 HRC are much less susceptible to hydrogen and to its effects. But as the material gets harder, the more electronegative materials get to the point where they're no longer able to pass and where they're having problems with hydrogen embrittlement. And ultimately what this means is that we can use the voltage to simulate the effect of hydrogen, and the hydrogen can come not just from cathodic potential, but also from corrosion and other mechanisms. So when the corrosion is occurring, it can induce a large amount of hydrogen into the material, and this gives us a way to quantitatively assess how much effect there could be from corrosion, external hydrogen, or from internal hydrogen in terms of embrittlement. So here's some examples of uses where step loading and stress analysis have been performed. That can be plating and coating, quality assurance, and testing. So this is routinely done on many materials in aerospace where we need to evaluate the possibility of internal hydrogen embrittlement due to the plating or coating processes. It can be due to exposure to chemicals. For example, the same method can be used to evaluate cleaning chemicals that are used on aerospace components to make sure that those chemicals aren't going to result in hydrogen embrittlement or other related failure mechanisms. It can be used in research and development, so for determining residual stresses after different types of manufacturing methods, for looking at stress corrosion cracking, and for determining true fracture toughness and fracture mechanics values, such as the K1 EAC value. And once you know those, you can input into your models, or you can use those in your design to ensure that you're maintaining your materials within an acceptable stress range. Then it can be used to evaluate galvanic and crevice corrosion. And finally, what we're talking about today, root cause failure analysis. So ultimately, this is really the next generation of how destructive testing is going to be performed, by doing it with smaller samples in a faster way and much more economically. So I really believe there should be a two-pronged approach to how we prevent environmental accelerated corrosion and failures. And the first is preventing the use of susceptible materials. So, for example, the Navy has done this extensively by using the step loading method to evaluate the susceptibility of all the different materials that they wanted to use. So they picked a wide range of high strength and corrosion resistant alloys, performed step loading, and then they were able to rank those different alloys based on real quantitative numerical criteria, and then that data can also be combined with modeling. They then limited the selections that they allow into use to only those that pass. And then the second part is preventing the use of susceptible microstructures or stresses or heat treatment. And the challenge there is that even when a material has been proven during step loading that it can be resistant to hydrogen embrittlement, that doesn't mean that it is every single time it's made. Due to variations that can occur in the processing or fabrication of materials, it's important that you also perform quality assurance in a routine manner that can help you make sure every batch that you're producing or that you're using is acceptable. And the advantage of both step loading and the stress analysis methods that I've presented are that they are rapid and economical. And that means that in production, instead of having to wait weeks or sometimes even months before you can use a component, you can test the component within the same day or within a couple days, and then be able to immediately start using the materials and have a much higher level of confidence in them. And then with the stress analysis, we can measure both the residual and the applied stresses on materials and make sure that they really are accurate in comparison to what we expect them to be, and that they're appropriate for the application. So here's another example, using the step loading method in comparison with the wedge opening test. So with the step loading method, we're able to find in a matter of 20 hours how long it took to determine the crack initiation threshold for this particular alloy, which is Aeromat22. And this testing was performed in a saltwater solution. In comparison with the traditional E1681 wedge opening load test, it took almost 10,000 hours to determine the threshold, so 14 months. So why would you do something in 14 months when you can use a sub-size specimen in the step loading method to tell you the exact same thing? So ultimately, as engineers, we want to design against crack growth. And what that means is we want the crack growth condition to be lower than the threshold for cracking. And we know that the largest, most stressed cracks are going to grow first. So the first thing we do is we look at the maximum flaw size that's acceptable, and that can dictate the design stresses that are allowable in a material. And then we look at the design stresses, and that can also go back and relate to the maximum flaw size. So you can use both of these, and with step loading, you're able to get quantitative numbers that can be used in these calculations to ensure that the design stresses and the flaw sizes are used appropriately so that you can accurately do your design and engineering in a way that you operate in the location where no fracture is expected to occur. And here's an example of a way that step loading has been used to speed up other types of testing, and that's perfectly applicable to failure analysis. So with traditional fatigue tests, depending on the rate and the number of cycles that are expected to be applied, it can take weeks or months to perform the tests. With step loading, you can perform the same thing, but only doing a much smaller number of cycles at each incremental step. And that means that you can rapidly determine the threshold where fatigue cracking would occur. And that can be the starting point for hydrogen-induced cracking and other things like that. And then we even have a method where we can combine these two tests with hydrogen charging so that we can look at how Fatigue would occur in locations or in circumstances where hydrogen is coming into the materials, such as when corrosion is occurring. So this can be effective for evaluating corrosion fatigue as well. And there is currently a method described in STP 1391 for how to do the rising step load version of fatigue testing. And here's the second example. For stress corrosion cracking, the alternate immersion test has been widely used for looking at steel and aluminum and other materials, and it's based on alternate immersion. So essentially, the materials are subjected to salt water for 10 minutes, and then for 50 minutes they dry off. And this cycle is repeated over and over every hour. With the step loading method, instead of waiting until you see a fracture occur, we can apply stresses, and then we can accelerate how quickly we're able to do the test. So instead of having to make a large number of samples that are then all applied with different stress levels, we can take a single sample and be able to quantitatively measure the stress threshold for stress corrosion cracking. And then based on that, you can do appropriate design and engineering. So ultimately, I believe that the testing should really quantify what the material performance is, and it should be done in actual or similar environments instead of just obtaining a qualitative comparison. So for example, using step loading, you can determine the K1 EAC value for fracture toughness, and that can be used to really accurately do design of your materials. With stress analysis, we can then combine the measured stresses with the fracture toughness values to much more accurately model failures. Because when failures occur in aerospace due to the high level of consequence, we often spend a lot more time and effort in really understanding how those failures occur and how to prevent them. And the combination of these two techniques gives you a much more effective way of performing the analysis and ensuring that the same type of failures don't occur in the future. And ultimately, we want test methods that are cost-effective and expedient in terms of time so that we can get a significant amount of data using a single standard machine or system. And both of these are standardized and have been used for decades now. Thanks for your time. If you have comments or questions, please contact me directly. I've included my cell number, and you can reach me at josh@uscorrosion.com if you'd like to discuss any of the details of this presentation. Thank you.